Calorimetry.
Huh?
Calorimetry.
What the Sigma?
Calorimetry. Heat measure. Welcome to episode 4 of Doing Physics Until I Get a Girlfriend. In this video, we're going to learn about measuring heat. There are two heat-related phenomena, each with their own equation. The first one is, if you add energy to a mass, the temperature changes. So now there's a central question. How much energy is required to raise a unit of mass by 1 degree Celsius? Well, it depends on the heat capacity of a substance. Water, it requires 4,181 joules of energy to raise 1 kilogram 1 degree Celsius. So we could say that its heat capacity is 4184 joules per kilogram degree Celsius. So let's look at the units here. The heat capacity is equal to the energy per unit mass times the change in temperature, which we can rearrange to get this equation here. Q equals mc delta T. The second heat-related phenomenon is that energy is required to change the state of matter. So that's the question, isn't it? How much energy per unit mass is required to change states? Energy per unit mass, we call that latent heat, and we can decompose the formula. Q equals the mass times the latent heat. So the answer is also, it depends on the substance. For water, it's 33,400 joules per kilogram. And for water, it's 2,265 joules per kilogram. So how are there two latent heats for water? Water has two latent heat constants because water can change states in two ways. It can perform this here, melt, freeze, or it can do this, evaporate and condensate. So the reason that there are 2 instead of 4 is because the energy required to melt is the same as the energy released when freezing. Yes, and the energy required to condensate is equal and opposite to the energy required to evaporate, because these two are equal and opposite. So we just call this thing here fusion and this thing here vaporization. The latent heat of fusion of water is equal to 33,400 joules per kilogram. The latent heat of vaporization of water is equal to 2,265 joules per kilogram. That's why there are two latent heat constants for water. In the same way that distance can be measured in meters and kilometers, the same way that mass can be measured in grams and kilograms, the heat capacity can come in all sorts of units. So if it's abnormally high, like in water, it can be joules per kilogram. If you have large samples, it can be kilojoules per kilogram. And if you're working with small samples, it can be joules per gram, even though these are the same. Because the kilos would cancel out. And if you're working with American units, it would also be different. So when you're doing homework problems, don't just look up what the heat capacity of water is, because it can come in all sorts of units, so just be careful and remember to check your units. Now that we know the formulas and the applications, why don't we start on the problem?
Oh my God.
142 kilojoules of energy is applied to 500 grams of water at room temperature, which is 22 degrees Celsius. What will the final temperature be?
Huh?
I'll give hints, so pause the video if you want to solve this on your own.
A few moments later.
We know that Q is equal to mc delta T, so we can rewrite that as mc temperature final minus temperature initial. So we have this, we have this, we have this, we have this. So now simply just plug and solve. awesome. You just plug it in, you solve, and if you follow the units, the joules and kilograms would cancel out. Celsius, Celsius, unknown variable, Celsius. It's in Celsius. All right, problem number 2.
Round 2.
How much energy is required to turn 2 kilograms of boiling water into steam? Pause the video if you want to solve for yourself. And there's the answer. All right, so now for a more complex problem. 334 kilojoules of energy are applied to 100 grams of water that's initially at 90 degrees Celsius. What happens to the water? So looks like we got I think it's Q equals MC delta T, right? Q MC TI TF. Let's see what happens. And after performing all those calculations, we are left with superheated water. At standard temperature and pressure, this wouldn't be the case. First, the temperature would hit a ceiling at 100 degrees Celsius. So instead of X, we put 100 degrees Celsius. And then the rest of the water would convert some of the water into steam. The rest of the energy would turn some of the water into steam. So let's see how much water is turned into steam. When we perform all the calculations after setting the ceiling, the mass that evaporates is 0.035. So let's see what would happen logically, right? Numbers don't really tell a story without, the initial word problem. So the first thing that would happen is all 100 grams would become 100 degrees Celsius. The second thing that would happen after it hits that ceiling is that some of it would become steam. 35 of 100. Awesome. And that's the solution to the problem. This is the last and most complicated problem of them all. Half a kilogram of room temperature water is placed onto a 150 degrees Celsius cast iron pan. If the pan's mass is 3 kilograms and the heat capacity of cast iron is 450 joules per kilogram degree Celsius, what will the equilibrium temperature be? That's a lot of words. But why don't we start with stuff that we know? Therefore, we know that the energy that the water gains, therefore we can write this as MC delta T equals MC delta T. The water that the pan lost is equal to the water that the energy that the pan lost is equal to the energy that the water gained. The energy the pan loses is equal to the energy that the water gains. Therefore, delta Q equals 0. No new energy enters or leaves the system. So why don't we set up our equation? MC delta T equals MC delta T. That's how I'd set up my equation. And importantly here, we see that T of F is on the left on the water side, and T of F is on the right of the iron side. Well, we know that the final temperature will be between 22 degrees Celsius and 150 degrees Celsius. So we know that it's going to be larger than 22 degrees, so it's positive. To make that positive, it's T of F minus 22. To make this side positive, it's 150 minus a number between 150 and 22. So simplify simplify the thing, distribute, do some very simple maths, and my final answer was 70 degrees Celsius, which makes sense because 70 degrees is between 22 and 150. Alright, well, the final notes are these are very important to memorize unless these are on like some data table somewhere. So all you have to do is memorize these two equations. Don't forget to dislike and report.